Okay, so we saw persistence diagram, how we obtain persistence diagram. Now let's look at the details of persistence diagram. So the idea is basically to keep track how the homology changes over the course of action. Okay, so given a filtration Fk, we get subcomplexes, yeah, until all are connected and become one single cell complex. So we have a sequence of maps of date homology class from HD from K0 until to HDK. As we increase, we will get various class of HDs. Right? So we can collect all this and then use it for machine learning. For each homology class that is born at I and dies at J, yeah, a 2-tuple I in R2 at I and J, and the collections are for B, for example, B1, D1 for date homology computation until BK to DK. So the D on top here, it can represent class 0, connected components, class 1, representing one-dimensional whole, and so on and so forth. And here we use a square bracket to signify a multiset. Yeah, a multiset. A multiset simply means it's just like a set, but we keep each element, yeah, each element, rather than just representing a simple set. Yeah, for example, in let's say in a basket, we have a collection of fruits. We have 2 apples, we have 3 oranges, we have maybe pineapple, 2 pineapples. So rather than saying that the set in the basket represents apple, apple, and orange and pineapple, we say we have apple A, apple B, and then orange A, orange B, orange C, A, pineapple B. So that is a multi-set. Yeah, we keep track of each unique element in the basket. Okay, so similarly here, we keep all the collection of the points, the birth and death points of the homology class, in which we then represent using persistent homology or persistence diagram. Okay, so persistence homology takes a filtered space K, yeah, K with some R, okay, for some R, and return diagram. So we denote as D of points of birth and death, which is in fact can be visualized in R2. Okay, so that is persistence diagram. Now we can calculate number of information, or we can summarize the shapes information in number of ways using persistence diagram. Yeah. Unfortunately, we cannot use the birth and death pairs directly into machine learning. We just need to align a little, such a way that we use the shapes information for machine learning purpose. So one example would be to compute lifespan. Lifespan is denoted as L is equals to the death minus the birth. So in fact, we can take all the collection of death minus death minus birth, death minus birth, and keep track of this all the lifespan of the death and birth pairs. So then we can use this information for machine learning. Persistent features with long lifespan are considered robust and likely to represent true topological structures, while short-lived features may correspond to geometric features. Right, just now we saw like big 2 holes which persisted over some time. So the big hole will be very far away from the diagonal line. For example, this very far away. This indicates the big hole, which is the topological information. So again, this small hole here, I mean, this hole here pretty much a bit further as well from the diagonal line also represents the topological information. Whereas the ones two diagonal lines A collection of them represents the curvature of the point cloud actually. Yeah, it is not noise. We cannot say this is useless, but we can in fact use that for machine learning as well. What this statement says, yeah, the with long lifespan are considered robust, whereas short lifespan represents geometric features. However, persistent diagram is not well-defined space which cannot be used directly for machine learning purpose. As I said earlier, example here, imagine all this space on top, yeah, on top of the diagonal line are birth and path dash, birth and path, yeah, birth and death pairs. Whereas the one below has no values of birth and death pairs at all. So this is not a proper space. Yeah, the space should be proper, means all the space are well defined. Whereas the one below diagonal line has no meaning for persistent diagram here. So we need to convert it into such a way that the space is well defined. Right? The process of converting persistence diagrams, but then that pass into a vector, it's called vectorization. So we will convert the D represents persistent diagram, into a vector. Yeah, this vector can be in any dimensional space from the two tuples of birth and death pairs, embedding them into a well-defined space. So this process is called vectorization. Right, so one example of vectorization is persistence landscape. Yeah, let me show the example first, the drawing. So this is the persistence diagram on the left-hand side. So what you do is that you convert it into a vector, right? So a collection of birth and death pairs. The first step is to create the 10th function. The 10th function, yeah, simple 10th function looks like a triangles. So taking this 10th function, then you rotate it 45 degrees. So you get in a new space of D plus B over 2 with x-axis, whereas the y-axis D minus B over 2. So when you convert, you get such a 10th function from the point, from the birth and death. After that, you keep track of the maximum values. The first maximum value can be represented in blue lines. The next maximum value can be represented with red. And finally, the third maximum value can be represented by orange lines. So the first line we can denote as lambda 1. The second line we denote as lambda 2. And the third line we can represent as lambda 3. So lambda 1 key, we can use it as feature 1, representing this point cloud. Lambda 2 as feature 2, lambda 3 as feature 3. So we have now 3 features representing the shapes information of this point cloud. So using this feature, we will then put into a machine learning algorithm, for example, classification, to do classification. Yeah. So that is the idea. Okay. And what is this vectorization is called? It's called persistence landscape. Yeah. Persistent landscape was introduced by Bubenic. It's a vector associated with Banach space induced by metric form, in which we can measure distance of elements within the space. The persistent landscape is a collection of continuous piecewise linear function, which is lambda, is the product of n times r, in which we get R, a line that summarizes a persistence diagram. The birth-death pair BD, which is in persistence diagram, we remove infinity point into a new space. B plus D over 2 representing x-axis, D minus B over 2 representing y-axis in R2, yeah, as shown in the figure in the next slide. The landscape is defined by the set functions created by the 10 of the rotated D as follows. So when you compute this, you would get a 10th function, a linear function. The persistent landscape of lambda p of D is the summary of the arrangement of piecewise linear curves obeying the graph's functions of lambda p of all the persistence diagram. Yeah, formally, the persistent landscape vector of D is a collection of functions. Okay, so the max, yeah, kth max lambda, yeah, k for the lambda, yeah, where t represents 0 to t, yeah, and where t is actually the parameter of 0 to t, and where k max is the kth largest value in the set. Yeah. Yeah. So the step again, just 3 steps. Yeah. First, create a 10th function, the triangular functions for each point, and then find the intersection. Yeah. Of course, rotate first 45 degrees to find the intersection, and then get the kth maximum layer. That's so each layer represents a feature. Okay, so that is how we do persistence landscape. Again, persistent landscape is the vectorization of persistence diagram, right? So this is the from the collection of birth and death pairs, and then of course we first create 10 function for each, and then we rotate it 45 degrees, and then the first maximum represents lambda 1, second maximum represents lambda 2, represents lambda 3. Okay, so this is the points. Yeah, we have like each point represents from 0 to 1000. We can change the resolution, in which I will show during in the lab video, in the Python lab video in a while. Okay, so lambda 1 can be feature 1, lambda 2 can be feature 2, lambda 3 can be feature 3 for your classification work. You can also create persistence image. Again, it's also a vector from persistence diagram. So rather than representing it in a line, kth maximum line, each point are now given a weight, a Gaussian distribution on the weight. So each point are given Gaussian distribution on the weight based on the height of the weight. And they overlap. Example here, there were a number of points overlap, so the weight increases. Okay, and this is actually pixels. Yeah, pixels from left to right. We have pixel number. So each pixel value are given based on the weight of the y value. So we get a persistent image. This persistence image can be flattened into a long, lengthy array, and that array would be the feature of this point cloud. And again, we can use this feature to do classification or clustering. Okay, so it was introduced by Henry Adams.